It's Akbar Barkesseh. For this topic, I'm going to explain about this different perspective and aspects of the arc fault that is suitable for electrical engineer or dealing practical cases for calculating the arc energy in electrical engineering concepts. It's not really in the physics or very high theoretical approach for that. So it's basically the arc voltage is influenced by several variables and is the most difficult parameter to evaluate. It's not the same in air as in oil or in SF6. So the very important aspect of the arc is arc voltage. I don't use arc resistance, and you see that why is that. The arc voltage is nearly independent of the current, dependent on the arc length is very important, and dependent on pressure. So basically the energy of the arc is voltage of the arc multiplied by current of the arc and multiplied by time. And if it's a kV, Ka, and second, the energy comes in the megajoule. And the power of the arc is just taking out the time is kV and multiplied by Ka is megawatt energy is releasing in the arc. Two well-known this expression for arc voltage in air is used in two protection relaying handbooks, and it's suited for us. One of them is Lewis-Blackburn equation, which is completely independent of the arc voltage, is completely independent of current, and is only proportional to the arc length, is regardless of voltage level or anything. And we have a Van Warrington equation that it has some sort of impact on the current, but is still proportional to the arc length. So for sake of simplicity and comparison and other activity we're going to do in this presentation, we only using the Lewis-Blackburn equations. So, okay, which is some proportionality to the arc length. So in normal case, in normal system, when we have a bolted fault current, we only have a source and source impedance. So the bolted fault current is basically this source voltage divided by source impedance. But if we have an arc involved on that, I put deliberately V arc, not I arc or I resistance. If we have an arc voltage here, then this bolted short circuit will be reduced to some value. And the energy of the arc is basically the arc current multiplied by arc voltage multiplied by time. So in this case, the arc voltage is basically the source voltage minus the arc voltage divided by the source impedance. And the arc energy is the arc current multiplied by arc voltage. And we gave this equation. And in this equation, if we put derivative equal to 0, then we have the value of arc voltage equal to half of the source voltage is when is the arc energy is going to maximum. So basically in this equation, you want to say that by increasing the arc voltage or arc length, the energy of the arc increased up to the point that the arc voltage reaching to the half of the source voltage. And the arc current at that point is half of the bolted fault current. And beyond that point, by increasing the arc length or V arc, that the energy of the arc will reduce. So basically, by increasing the arc length to some point, we're increasing the arc energy. And if passing that point, which is half of the source voltage, decreasing the arc energy. But I just want to, with this example, say that we're not, in credible cases in electrical engineering, we're not reaching to this point. We always below this point. So we can, with some sort of confidence, say that in credible cases in electrical engineering, by increasing the arc length, the energy of the arc always increasing. And just for some proof of that, I just using Lewis-Blackburn equation and calculating the arc length that gives the maximum energy. So for 400 volt system is half of the system voltage divided by 1.44 from this equation, and it's 160 millimeter of the arc length. And for 11 kV system, it's going to 2.2 millimeter arc length. Both of these values, if we know the clearances in the LV is in the magnitude of 30 or 40 millimeter, so we're not going to the arc that's short circuiting two gaps over the gap 40 millimeter reaching to 160 millimeter arc length. It's not credible. So basically now we can with some sort of confidence say that for credible cases, increasing the arc length, increasing the energy. So what is the expected arc length? So arc length, we can say minimum and the maximum arc length. What sort of idea we can have for that? The minimum arc length basically is the clearance. So the minimum clearance distance. So if you have a conductor here and enclosure here, then we have a minimum clearance distance, the shortest distance between them. So that's the arc could not be less than this distance. Basically, it's very obvious. And just because I said this presentation is about the concepts, IEEE 1584, it doesn't say the minimum arc length and something like that. It actually introduces some standardized gaps in LV system and the HV up to 15 kV. So what it does now, we know that it wants to actually some sort of standardized length of the arc for different equipment or different condition. So basically, he said in IEEE 1584, he said between 15 to 40 millimeter is open air we expecting to this distance. In switchgear, we expecting 32 millimeter of this distance. In panels is 25 millimeter, and the cables in 13 millimeter. And you see even in the HV system, up to 15 kV, you see that it doesn't touch the value of the cable. So it's now we're understanding why it is standardized. It wants to get some sort of credible energy value for equipment. It doesn't want to say get some energy value of very high in a cable, which is not practical, which is not credible. So now we're understanding why it's standardized the gaps in IEEE 1584. And beyond the 15 kV or any voltage level, what is the minimum distance? The minimum distance basically dictated by the minimum clearance that required, which normally comes extracted from basic impulse level of that voltage. So basically we have equipment here like transformer and bushing or post insulator and the conductor here. This minimum distance between conductor and the enclosure is dictated by basic impulse level, by BIL level. So for example, in 11 kV, if we choose 95 kV BIL, then this distance between phase and ground is 160 millimeter. So, and also you see the 466 as 20 kV. Based on the selected BIL, we have some sort of minimum distance between phase to ground and phase to phase. So how about the maximum arc length? So we have some sort of idea about the minimum arc length. How about the maximum? Arc has tendency to increase its length due to high level of electromagnetic force. Arc has tendency to increase its length. Why? Just having some quick here. If you have a U-shaped conductor, basically parallel conductor could be in and out current, and they are in opposite direction. They actually repelling each other. The two conductor repelling, put a force outside of each other. So if we look at the random shape of the arc length, you can identify several type of the sort of U shape in alongside the arc length. So any of these U shape, for example, this one is like this, creating some force. And you know that in the arc we have a very high current and high magnetic forces. So this force and this force cause that the arc length to increase. So arc by nature have this tendency to increase its length. So how far it can go, the length of the arc. In some guides or handbooks, they recommend that maximum stable length of the arc could be twice of the minimum one. So I really don't know really the background of that, but we can have something in place somewhere is recommended to can get the stable length of the arc because it cannot is from some length it could be unstable. So the stable maximum arc length is actually twice of the minimum one. So basically, with this sort of idea that we have, is we now can have a comparison between arc fault current in HV and LV, why they are different. Because after knowing some sort of characteristic of the arc. So let's say both HV and LV system have both of them 25 kA fault level, and the HV LV system is 400 volt system has the minimum or clearance of 32 millimeter. 32 millimeter, which that one in IEEE said for switchgear. And also the 11 kV, again, from BIL level, we just getting 160 millimeter. So first thing, we calculating source impedance for these two system. In the LV system is a 400 volt phase voltage divided by 25 kA is 0.00925 ohms, and for 11 kV is 0.254 ohms, which is gives this 25 kA. Arc length, based on this recommendation, for sake of simplicity, we're not going to IEEE something, we're just using this just because we're going to comparison. Twice of the arc length, so twice of the arc length in LV system is going to be 64 millimeter, and in 11 kV twice of 160 millimeter is 320 millimeter. So now we're calculating I arc, so using the Lewis-Blackburn equation. So 400 volt phase minus arc voltage with 64 millimeter arc length divided by source impedance. Then we're seeing that in 400 volt the I arc is reduced bolted fault from 25 kA to 15 kA, which is 40% reduction of the short circuit, or 60% of short circuit, bolted short circuit. But whereas in 11 kV, the 25 kV original short circuit level by arc is reduced to 23 kA, and almost only 7% reduction of the short circuit level. That's one of the big difference in HV and LV. So in LV's HV system, I arc is approximately I bolted short circuit, but in LV, I arc could vary even from 30% to 60% of I short circuit bolted. And that is one of the big challenges in LV system, because in LV system, protection devices are simple over current. So we don't have a complicated, expensive protection system in LV, it's only over current. And imagine if you have a 30% of bolted short circuit current and it is an arc in place. So normally it's very hard for these devices to clear the fault in a proper way, in a proper delay. And some of them even cannot even detect any fault, whereas a massive arc in place. So I'm not going into detail on that, but say common mitigation against arc fault is a very broad topic, just very small touch here. That some sort of active mitigation by implementing additional insulation and dividers to make system arc sort of arc proof, such as using insulated bus bar or double insulation or other approaches. Is a passive mitigation which is normally used by reducing either magnitude of the I arc or reducing the clearance time, or basically magnitude of I, changing the I, reducing the I, or reducing the T time. Something like high speed light sensors that use targeting to reducing the clearance time, arc quenching devices that deliberately introduce bolted fault short circuit to extinguish the arc. That's another approaches. and also current limited devices targeting to reducing the magnitude of eye arc. All they are used kind of a passive mitigations. As I said, many of them is a very broad topic. I don't want to go ahead in that. So at the end, we're going to have two aspects of the arc, two hazards of the arc. One of the hazards, very well known, is heat. Excessive heat can burn people, death, casualties, and equipment, fire. It's a very well-known hazard of the arc. But what is this when you are calculating the energy in terms of megajoule at the point of the arc? When you're getting distance from that point, we receive less energy into our body or people that are from certain distance, basically in inverse square of the distance. If we inverse of a square is the distance, you get the distance away, you receive less energy. So what is the standard distance from the arc? So IEEE 1584 introduces the standard distances from the arc in different voltages. Not going to that, but you see for LB switchgear 610 millimeter, for MCC's cables 455 centimeters. Sorry. So and then based of these standard differences, but it's very important to know that the standard distances based on, if you be closer to the arc than this, then the energy that you calculated is not valid. So you need to zoning the area, which is a very broad topic in detail. Based on the calorie per square centimeter energy from a standard distance, adequate category of personal protective equipment, PPE, for handling arc heat are selected. Also zoning around equipment for identifying energy and PPE categories. Part of this practice is a very detailed practice, but basically both this one is dealing with the excessive heat from the arc. The other hazard of the arc, which is not very well known among engineers, is explosion. In addition to heat, arc has the explosion, can create the explosion, and this kind of a pressure wave could damage the structure, could damage the wall, and bring some sort of hazard to people, to collapsing the buildings somehow or equipment, and that is different from the heat. It's a explosion. So in normally the explosion is being looked after or very detailed by switchgear manufacturer. Switchgear manufacturer is very well known about this phenomena. When they want to build manufacture the switchboard which is arc rated, they really wanted to control the explosion wave and pressure wave and keep the structure intact, the switchboard intact, and direct this pressure out of the switchboard. So from switchboard manufacturer is very well known as the main thing that they are dealing with to make a switchboard which is arc rated. But apart from switchboard manufacturer, other engineers are not very well familiar with this aspect. So arc is creating pressure wave and is act like explosive. From energy point of view, 4.2 megajoule of energy is equivalent to 1 kilogram TNT or dynamites. However, this energy is not the only parameter in destruction. Destructive power is not only the energy, is energy plus the rate of release of energy. Rate of release of energy together with energy determine the destructive power of explosion. So electric arc in air could have in the category bringing this. So you may have some sort of equivalent TNT value from the arc based on the energy that they're releasing, but in destructive power, that's a fire engineer or to model that in a proper way, and the speed of release of energy. So the speed of release of energy in pressure vessels is higher than the dynamite for TNT and dynamite from electric arc they are, different speed, release of a speed level. And for nuclear explosion, it's much faster than the others. So if you have a certain megajoule of energy releasing from the nuclear explosion, has rate of release of energy is much higher in terms of nanoseconds compared to electric arc or dynamite. So even with the same energy, the destructive power as nuclear is much higher than the others. But that's not because of energy, it's because of not only because of energy, it's because of rate of release of energy. So just want to say when we're dealing with the explosion, we need to deal with the energy and the rate of release of energy. So if, for example, in transformer oil, we have a lot of energy releasing in the arc inside the windings, it's ruptured the tank, but the rate of release of energy is not very fast and is in the category of deflagration, not detonation. So it it can create a massive fire, but when there is in the inside the oil, but cannot actually create blast. Mostly, it should be divided. But in electric arc in the air can create explosion wave pressure and destruct building structure, especially arc fault and the HV bushing of the indoor transformers. So arc fault in the air has this capability to create the explosive forces to the building. So basically what we are going to do, electrical engineers should give the energy releasing the maximum expected release of energy in the any point that they expecting to have arc and give that energy to the fire engineer. They are modeling that with some sort of equivalent TNT or whatever they are doing. Then they in their model they put some sort of explosion at that point, and then they calculating the kPa pressure on the walls and doors and cooling dampers and other equipment, and then they will give this value to the structural engineers to design properly the building. It's very important. I've dealt with many of these cases that either the wind explosion damaging, collapsing the building. And most of them has been overlooked by engineers. They didn't actually not. They just put a 2 hour fire rated wall around transformer. 2 hour fire rated wall is okay. It's protect from the fire, but explosion is different. And in some specific cases, especially indoor transformers, could create this massive pressure wave and like explosion of bomb inside the room can damage collapse whole building. I hope this presentation helped you to understanding the basic phenomena, especially about the arc, and have better idea understanding the standards. They have a very detailed. This is a very detailed topic, and you may have some challenges or engaging to giving recommendation to reducing the energy or different approaches, but it's better to know the fundamental of that. Thank you for watching, and bye bye.